So there are a few terms, I am calling them concepts, that you need to understand when we are looking at the problem of DMA, or rather the usage of DMA, right. One of them is what is called bus mastering, and bus mastering is essentially the idea of a bus master but converted into a verb, right. We basically bus mastering by itself does not make sense, but we verb words, right. We basically take something which is a noun or an adjective and then convert it into a verb just because it is convenient to talk about it that way. So bus mastering essentially means becoming a bus master, right. In other words, the DMA controller initiates memory transactions. Now we have already talked about the concept of physical addresses and virtual addresses before. We know that because of memory protection, memory management, multiple processes and so on, operating systems use virtual addresses. And there is one very tricky thing that you need to understand over here. It is sort of natural to say, okay, so my addresses are all virtual inside, I am anyway working inside my operating system, I need to basically perform a data transfer, just use the pointer that I have inside my code and give that to the DMA module. The interesting thing over here is, remember where the DMA is on the bus, right. If we look at this picture, the CPU is the one running the operating system, it is the one that is basically controlling all these other peripherals. The DMA actually does not know of the existence of an operating system, right. So when you tell the DMA that it needs to transfer data, it should be given physical addresses, not virtual addresses, because it does not by itself have a way of translating a physical address to a virtual address. That translation is usually stored inside what are called TLBs, translation look aside buffers, inside the CPU. If you have an SoC where the DMA is also part of it, potentially the CPU, you may have access to some things of that sort, but in general the idea is that the DMA is a separate module outside of the core CPU, it is not part of the CPU core itself, right. Which means that when it needs to transfer data from A to B, it needs to know the physical addresses of A and B and not their virtual addresses, right. So this is an important thing to keep in mind when we are actually programming the DMA. Cache coherency is another important concept that we will talk about a little bit more, and we need to basically ensure that when there is a problem of caches, the CPU and the DMA must see the same data. And one more useful concept in the context of DMA is that they make extensive use of interrupts. It almost never makes sense to do DMA and then poll for the completion of DMA, right. It beats the whole purpose of the DMA, which was to free up the CPU, right. So instead what we do is, whenever we use DMA, we usually couple it with interrupts so that the CPU can do something else, but as and when the DMA has completed its work, it signals the completion via an IRQ and the CPU can then go handle it, which might even be as simple as saying, okay fine, yeah, thanks for transferring the data, nothing more to do right now, okay. So as we get a little bit more into the details of how exactly this gets implemented in the hardware, I just want to sort of refresh one concept on the notion of stream data, right, the AXI-Stream. Now this is a picture we have seen earlier, it essentially is talking about the valid ready handshake, right. This is in the context of, let's say, the write address or the read data that we are talking about, where we are basically trying to send the addresses or data. But the point is that this valid ready handshake is actually a very powerful concept on its own, right. And in fact there is an entire sort of version of the data transfer which follows this concept of what is called an AXI-Stream, right, where I have some data that I want transferred, right, and this would typically be a bus, let's say a 32-bit bus. Whenever I want to send data in, I accompany it with a valid signal, right, and the idea is that I need to have a T ready that is coming out of this module, let me call it B, that I have over here, right. So I am transferring data from A to B. A is trying to send data to B along with putting the data onto this bus, which means that basically setting the signals of T data of 31:0 to the zeros and ones that I want to transfer. I also take the T valid signal, which is again under A's control, and make that equal to 1. Now it's not just for one clock cycle, I actually need to sort of make it one and hold it until B makes this ready signal high, right. So when B makes a ready signal high, I say okay fine, now I have transferred one word of data. Maybe I have only one word, in which case I immediately make the valid signal low. But the interesting thing about the stream is I could potentially also keep this high and continue transferring data. On the next clock cycle, all that I need to do is change the T data to its new set of values, and without sort of skipping a beat, without losing any cycles, I can transfer 2 data in 2 clock cycles, or 3 in 3 clock cycles, 4 in 4 clock cycles, and so on. Provided A and B have been designed properly, this handshake should work perfectly. I should be able to transfer like data at extremely high throughput, right, because on every clock cycle I transfer one word of data. Now the handshake itself could also happen differently. I could make the valid high, the ready goes high, but then it immediately becomes low after that, which means that B is not ready to accept more data, right, even though A has data, right. So A is sort of saying, hey wait, I have some more data that I want to transfer, but B has immediately made it low over here. So after some time A, for whatever reason, stops, right, but it basically cannot send any more data out here, right. It might, after doing some further processing, once again make it high, or it might just hold this high until B is ready to accept new data again. So all of those are possibilities. The point is that if we use this handshake where we have the data, or rather the valid signal and the ready signal which do the handshake, and we actually use data to send the payload, right, we can consistently transfer data potentially on every clock cycle. Now for something like an FIR filter, this is great, because what it means is B could be the filter, and on every clock cycle I can receive a new sample which I need to process, and on the other side I could basically give out a new sample, right. The interesting thing also is that because of the handshaking that we have over here, B could then be sending data somewhere else, and the other side could say wait, I am not ready to accept data yet. It will essentially make its ready signal low, right. So even though there is a valid signal coming out of B, the ready signal coming from, let's say, C, right, when it becomes low over here, it means that B has to stop. It cannot try and send any new data out here. It has to sort of hold the valid signal, but it cannot keep changing the data, right. And in that case, most likely B will, after some time, depending on whether it has any internal buffers or not, send back a signal to A saying, wait, I am not able to get rid of my data, so you also need to stop. It will say T ready is low. A has to then wait. This process is called back pressure, right, which is a very powerful idea when you are sort of chaining systems together and trying to build high throughput applications. Now as far as we are concerned, the FIR filter is a perfect example of a streaming data, right, where I want to just sort of continuously send data one after the other. The biggest difference, as you might have noticed over here, is I have data, I have valid, I have ready, I do not have an address, right. So I am not trying to write into a specific address inside B, I am just giving data as input to B. That is what happens in a filter, for example, right. I do not really care about the address into which a particular data is written. I am saying this is the next sample, next sample, next sample, that is all, you need to process it. So when we have this kind of stream, this actually plays very well with things like DMA. I could potentially have something where I have a chunk of data sitting in memory, and I tell the DMA read out the data one by one and then just send it out on a stream, okay. And this in fact is a very common use case, and therefore DMA is sort of has some specific features which enable that, right. So just to recap, why exactly do we use AXI-Stream? Mostly for continuous data, right. For example, samples from an A to D converter, video data, network. Network is potentially, it's not real time in the sense that I don't have deadlines saying by this time I need to get rid of this packet, or most of the time we don't. But it is still large enough volumes of data that I could think of it as, a chunk of data that needs to get transferred. The nice thing about it, as I mentioned, is it has a very natural flow control, and the framing. The framing is actually related to one more signal in the stream which is called the T last, which allows me to indicate the end of a packet. Very useful for network applications, for example, not necessarily for things like A to D converters or video, where you know exactly Either you know that you have an infinite stream of data, or you know exactly ahead of time how much data is going to be there. But the streaming transfer is a very powerful utility, right. So AXI DMA, as I said, is the DMA direct memory access which is implemented on top of the AXI bus. In particular, the one that I am going to be referring to is this part of the DMA which refers to the Xilinx IP blocks, because that is what we will be using in our demos, right. And what happens over here is those the IP blocks essentially have a way by which they can take a chunk of memory, a sequence of addresses, and convert it into an AXI stream. So in other words, my peripheral, right, my IP block corresponding to the AXI DMA, and this is something that has been created by Xilinx and is provided as a IP ready to use, will take care of this thing where I can tell it, okay, take data from this chunk of memory and then send it out on an AXI stream, right. It basically will take care of the valid data, T last, all of those, and wait for the T ready that's required in order to do the transfer, right. It can also do the opposite, which is to say it can accept data which is coming in from an AXI stream. It could be the output of a filter, it could be data coming in from an A to D converter, and basically say consume by sending out an appropriate T ready signal, right, wait for data to come in from the other side, and as and when there is valid data from there and I have given out T ready over here, consume the data and store it into successive locations in memory, right. So this gives us a very nice sort of IP to work with and a nice programming model that we can build around, right. And the way that we use it in general will be that we need to write the physical source and destination addresses. Note again that it's physical. DMA does not know about virtual addresses, so I need to use physical addresses, and I just basically write one parameter to a length register in order to actually start the transfer, right. And the DMA module automatically asserts what's called a T-last signal at the end, right. As I said, the T-last is used for framing to indicate the end of a packet. It's just a 1-bit signal, but very useful, because if I, for example, tell length of 16 words, right, the DMA will automatically go through, transfer 16 words, and on the last word it will make the T-last signal equal to 1. The interesting thing is, what that means is the destination, whoever is receiving my data, does not need to know in advance how many data I am trying to transfer. I don't need to say, okay, wait, I am sending 16 words, here's the first one, and so on. I just start sending data, and the receiver starts accumulating the data, and as and when it sees the T-last equal to 1, it knows that the packet is completed, right. And of course, given that we are putting all of this in the context of an SoC, right, we have a DMA module attached to a the CPU core and so on, we enable IRQs and wait for completion, right. So this is basically how we would use it in practice, right. There are a few implications of using DMA in this manner. The memory map to stream, right, so this is where we are reading from memory and trying to send it out on a stream, that is limited by the downstream T ready. What does that mean? It means that the peripheral into which I am trying to write data, might not be able to consume data as fast as the DMA can send it, in which case it might send T ready back, make it low at some points, and the DMA has to stop. So the DMA might not be able to transfer data on every clock cycle. It's intelligent enough to know how to handle that, right. It will actually release the bus on those occasions. If necessary, the CPU can then come in and do other work, right. So all of this gets handled very nicely by the way that the bus is designed. Whenever the DMA is not able to actually do a read or write transfer on the bus, it can release the bus and let some other bus master, the other CPU probably, or maybe if there are 2 CPUs in the system, one of the other CPUs take over and do some other transfer. S2MM writes only when upstream T valid and T ready. Now what that means is you could have the opposite problem, which is that your peripheral, the stream that you are reading from, is sending data too fast, right. You want to push back pressure it and tell it to slow down. You can do that because you now have a T ready which is in your control through the DMA module, and it can always synchronize and make sure that all the data gets into main memory without being lost, right. And once again, what you can do is that you can split the data that you have over here into frames. So for example, if you are receiving data on, let's say, Ethernet packets, it's coming in as an AXI-Stream, but by using appropriate T-last signals, you can actually indicate, okay, this was the end of one packet, this is just, and immediately the next transfer is the start of the next packet, and so on, right? So there are like, both of these are very well co-designed, right? You can use them together quite nicely for a good way of transferring data around.